Hey guys, welcome back to Pop 'em Up Chem. In this video, we're going to be looking at orbital theory and how to draw out electron configurations, kind of building on what we did with the hydrogen spectra and explaining the complexities of electronic structure. In this video, we're going to be introducing orbital theory, some of the shapes, and how we can formulate the configurations. But for now, pause the video and have a go at this question on convergence limit from the last video. So in this question, first we pick up that we've got nanometers. So we're going to times 10 to the power of minus 9 to get our meters. And then we're going to do V equals C over lambda to do speed of light over our wavelength, which is going to give us our frequency, which is 1.24 times 10 to the minus 15 per second. Then we use our E equals HV equation, and remember H is Planck's constant, which is given in the data booklet, multiplied by the value that we got in the first part, which gives us 8.22 times 10 to the minus 19. Now, the question says in kilojoules per mole, so I know I'm going to need to convert this into moles, and so for that I'm going to use trusty old Avogadro's constant, multiply those, which gives me my number of joules per mole. Obviously then I need to divide that by 1000 to get my value in kilojoules per mole. So let's address what we're looking at today. We might be asking why we even need to further describe this. We already looked at the hydrogen emission spectrum and the transition between the orbitals. Well, the problem we have with that is, apart from hydrogen, which follows it very well, when we start looking at other elements, we actually start to see these discrete levels split, and it's not quite as simple as n equals 2. We see that n equals 2 has a couple of sub-levels, n equals 3 has 3 sub-levels, n equals 4, for example, has 4 sub-levels, and so on. The point being is that although we can still group these as discrete energy levels, we need a model that can describe the splitting of these energy levels into further sublevels. And this is where orbital theory comes in. So what's an orbital? Well, all an orbital is a region of space, a place where we can describe it as being highly probable that an electron exists. In this way, we're considering an orbital as a probability. So this theory stems from Heisenberg's uncertainty principle, with the evidence at the turn of the last century that you couldn't determine both the position and the momentum of an electron. Einstein was famously quoted as saying, "God doesn't play dice," in response to this, believing that we would eventually find some kind of way of measuring both of these properties. Unfortunately, until this day, we still are yet to be able to do that, and this theory holds with a lot more evidence that's grown over the last century. So we needed a new model to build on this simplistic Bohr model of rings around the nucleus, and that's where orbitals come in. So orbitals come in 4 main types. That's S, P, D, and F. We're not going to study F at IB level. They all have different shapes. S orbitals have a simple spherical shape, which I haven't drawn very well here. P orbitals exist around 3 different points. If we think of the nucleus at the center of this axes that I've drawn here in the X, Y, Z plane, if we think about the nucleus in the center, then there are 3 p orbitals, and they can be arranged with respect along one of each of the axes, if you like. So we can have the different dumbbell shapes that they form, kind of they're larger on each side and then going across the nucleus along that axis. The d orbitals are slightly more complex, but there are 5 of them. You do not have to be able to remember to draw the different structures or name the different structures of the d orbitals, and we will look at the d orbitals in more detail when we do unit 3 and 13, when we do the higher level component there. But we have 3 kind of 4-pronged dumbbell shaped orbitals that exist between each of the series of axes, and then we have 2 orbitals which exist over the top of the axis. We have one with this kind of donut going around the middle and then a dumbbell in between, and then we have one that is also kind of a 4-pronged dumbbell shape but going along the axes. So there is one s orbital in every shell. There are 3 p orbitals in every shell apart from the first shell, so from n equals 2, and 5 d orbitals in every shell from the third shell. However, as you may have noticed, I'm no artist, and lots of other chemists aren't too good at it either. Apart from anything, this kind of representation obviously takes a long time and doesn't lend itself well to an analytical perspective. So that's why we instead tend to use electron-in-a-box diagrams or electron configuration, which we'll cover later. These represent orbitals as boxes, which can each contain 2 oppositely spun electrons, and we group types of orbitals together. So you'll see here I've got the p orbitals together, I've got the d orbitals together, and the s orbitals together, and then they are grouped by energy level. Okay, so how do we start filling this up? Well, we first want to have a look at the Aufbau principle, which the electrons should be placed in the lowest energy orbital first. This may seem common sense. You can't start on the middle step or fill a cup of water from the top down. You always have to fill from the bottom up. And the same is true for electrons. If we have 2 electrons, we can't just put them further up. We have to fill the lowest energy shell first. So far, so common sense. However, there are a couple of other principles we need to take into consideration when we're filling up our electrons. And these are the Pauli exclusion principle and Hund's rule of maximum multiplicity. Don't worry about all these rules, we only have to be able to do the process. And all they really mean is that electrons repel each other, which is going to drive the position that they go into the orbitals, and that no electron can have the same position, if you like, in the orbitals as another electron. Its spin or its energy level or its orbital must be different. The point being is we have to consider that electrons are negatively charged and they repel each other. So although between energy levels, completely fine, we just add electrons to the lowest energy level, what about when we're inside an energy level? How does this affect them? Well, if we look at filling up our p orbitals, we put 1 electron in each orbital first before we pair the electrons. And that's because when we're filling the orbitals, it can take energy to flip the spin of an electron and to pair an electron with another one. So when we fill orbitals that have the same energy, then we put them in separate orbitals to minimize that repulsive energy. If it's possible, doesn't matter. If it's not possible, then they just get paired up. That's fine. So what we would not see if we were trying to put a third electron into this p orbital was if we took that electron and we put it into this first orbital as paired, because there's going to take some extra energy to do that process. And there's a free orbital there, so the electron would go into the empty p orbital. So let's have a look at some examples and how this can be used to help us draw the electronic configuration. So I've got my electron-in-a-box diagrams on the left, and I've got this kind of visual mnemonic that I think can be really helpful for helping us. So here I've just written 1, 2, 3, 4, 2, 3, 4, and 3, 4 in rows. And then I've written S next to the first row, P next to the second row, and D next to the third row. These all represent orbitals. At the top in this example, I've given how many electrons fit into each orbital. So every orbital individually can only have 2 electrons, but we have one orbital that is s, so that's 2 electrons, 3 orbitals that are p, that's 6 electrons, and 5 orbitals that are d, which would be 10 electrons. So the way this can help us is following these kind of aquamarine arrows gives us the filling order of our atom. You will not be given your electron in a box diagram in a question in an exam, and you may be asked what the electron configuration of atoms are without any help. And this very simple to write down mnemonic will work for all of the examples you'll be looking at within the IB. So with carbon, for example, we have 6 electrons. So we're going to follow our arrows. So we first have our 1s, got 2 electrons there. So got 4 electrons left. Follow our next arrow is going to take us through the 2s, leaving us 2 electrons to go into the 2p. Now remember, you can't fill all 6 spaces here. So you're not going to put the electrons together. Instead, you're going to separate them and have them in their own separate p orbitals. So looking at the example of silicon now, a few more electrons here. We've got 14. So following our arrows, we still have the 1s2 and the 2s2 once again. Going through the 2p, we actually have enough electrons to fill the whole 2p. So we get 2p6 here. And then we go through the 3s, which leaves us 2 final electrons, which go into the 3p. Just like it was before, but with 1 electron shell up. Now, those electron in a box diagrams are great, but they do take a while. And so we can actually simplify this even further by writing out our electron configuration. Here, we're going to use the same visual mnemonic and just use the same way it's written in the visual mnemonic, but with a superscript that denotes how many electrons are in each orbital. With the example of beryllium, we're going to have 1s with 2 in it and a 2s with 2 in it, because we have 4 electrons overall. This is our electron configuration. So we can also try it with an element that's a little bit more complex. Let's try potassium, which has 19 electrons. Following the same rules, going through our diagram, we get 1s2, 2s2, that's 4 electrons, 2p6 is 10 electrons total, plus 3s2 is going to give us 12 electrons total, 7 remaining. Going down to the 3p, we know we can have 6 there, so I have 1 electron remaining, and I go into my 4s1. Simple as that. I just need to know this diagram and the number of electrons in each orbital. And if you want to get really lazy, as I often do, we can actually use the noble gases as our condensed configuration. This is obviously the configuration of argon plus 1 electron. You do not have to use condensed configurations if you don't want to, but I'll use them as we go on. One quick question just before we get on then. Have a go at doing it for the fluorine atom. Pause the video to give yourself some time for that. Pop them up! So using the same technique we did previously, we use our diagram to fill in 9 electrons. So we get 1s2, 2s2 to give us 4, 5 left. So we've got 2p, but we can fit 6, so we're only going to write 5 as our superscript. And that's it. So when we do the electron configuration of ions, we need to consider that negative ions have obviously gained an electron, they've become more negative, and positive ions have become more positive by losing an electron. So when we consider their electron configuration, we need to adjust the electron configuration notation accordingly. Take the example of sodium. We have 1s2, 2s2, 2p6, 3s1. If we have the positive ion, it's removed an electron, so we just take that 3s1 electron away, so the whole configuration ends at 2p6. With chlorine-17, we have the same configuration, except once we get to the 3 shell, we have 3s2, 3p5, and if it gains 1 electron, then we end up with the 3p6 configuration. Lastly, we're going to have a look at the first row transition metals. So they lie in between the S and the P block on this first row. And it's going to be helpful for us to consider that we always fill the 4s orbital when we draw the electron configuration. In reality, this 3D shell doesn't have a higher energy than the 4s shell, but this assumption helps with predictions. Indeed, it's due to complicated interactions between the repulsion of the d orbitals when we add electrons to them, but that's not important. The best way for us to model it is to think of the 4s shell as having a lower energy than the 3D shell when we add electrons. So let's have a look at the very first one of these elements, scandium, and see how we can apply this. So with scandium, we've got 21 electrons, so we're going to go through the whole process that we've gone before, following our diagram down. It's good practice to practice this, so we get 1s2, 2s2, 2p6, 3s2, and 3p6. So we've used up 18 electrons so far, so we still have 3 electrons remaining that we're going to add, and we always add them to the 4s first and then 1 in the 3d. So we follow our arrows down and it follows the diagram that we've been using all along. In fact, just filling up normal transition metals, no ions, is going to be exactly the same. So we're going to get argon, 4s2, 3d1. Looking at another simple example of iron, already filled in the bottom layers here, those first 18 electrons, just to speed it up. We've got 26 with iron, which gives us 8 remaining. So we're just going to fill up as we did before, and remember, add 1 per orbital first, 6 in the d orbital, so we're going to have an overall electron structure of argon, 4s2, 3d6. Now, when we want to write ions of the transition metals, we have to be careful. We have to always remember that that 4s orbital is actually the highest energy, and so we're always going to remove electrons from the 4s shell before the 3d shell. So we can have a look at cobalt for an example, which is 2+ here. But if we just write out the full electron configuration of cobalt without the charge first, so to write these top 2 shells, then we have our first 18 electrons, we have 9 electrons remaining, so we're going to have 4s2, and then we're going to fill in our d and have 3d7. Now, to take in consideration these 2+, we have 7 electrons, but instead of taking the 2 paired electrons away from our 3d, we're going to take those 4s electrons and leave all of our d electrons intact, because we always take those 4s electrons first, and so that's going to give us argon simply with 3d7. So we can have a look at examples of ions that may remove even more than just from the 4s. So let's have a look at vanadium 5+. Do the same thing again. I'm going to write the electron configuration as if it wasn't an ion. So I'm going to take the 18 electrons. I've got 5 left over, which give me 4s2, 3d3. But I need to take 5 electrons. So I'm always going to take those first 2 4s, but I still need more electrons. So indeed, with vanadium 5+, I'm going to take all of those. And so that's actually going to leave me with just argon as an electron configuration. Awesome. So there are 2 exceptions to this that we have to consider, and we're going to use the model of half shell and whole shell stability to be able to explain these variations in electron configuration. As I said before, that's just a model for us to use to be able to write the electron configuration. It isn't necessarily the case that the full shell is always more stable or the half shell is always more stable, as we would see with other elements further down the periodic table. but for copper and chromium, it'll do us just nicely. So let's write out what the electron configuration we would expect copper to be. So we would have 11 electrons left over after our 18 up to the 4s. So we would have 4s2 3d9. However, what copper notices, well, if it could notice, it can't notice, it's not a sentient being, but if it could, it would realize that it could move one of its 4s electrons up to its 3d shell and instead have a 4s1 3d10 configuration, which would give it one full shell and one half-filled shell. Similarly with chromium, after we place those first 18 electrons, we have 6 remaining, which would give us 4s2 and 3d4. But chromium, being savvy as it is, realizes that instead of having a 4s2 3d4 configuration, it can move again one of its 4s electrons up to that 3d shell, which is going to give it one half-filled 3d shell and one half-filled 4s shell. That means that it's not going to have that 4s2 3d4 configuration. Instead, it's going to have AR 4s1 3d5. So guys, you want to make sure you get some practice in. I suggest this electronic configuration worksheet first. No other videos for you, but a good bit of practice here, as you'll pick it up quickly if you do. Thanks again for joining me. Don't forget to like, subscribe, and as always, practice makes slightly better.